Okay, so recall that we had talked about what NP complete means. A language is NP complete if it has these two properties. First of all, it has to be in NP, so we have to show that it is verifiable in polynomial time. And then this perhaps trickier one, that we have to show that every language or every problem in NP is polynomial reducible to this one that we're trying to show is NP complete. Okay, and that second category is called NP hard. All right, now, so in order for us to do these kind of proofs, we need to have a kind of a first language where we can show that all the languages in NP are reducible to it. That gives us a starting point, and then when we do other reductions, it kind of gets, well, if that one can be reduced, we have this one starting place, and we can get a mapping that hooks them all together so that everything can be mapped to, so every problem can be mapped to another problem. Okay, and so the first problem that we need to look at that we're going to show is that all the languages in NP are reducible to it are the circuit satisfiability. Okay, so circuit satisfiability deals with Boolean circuits. So a Boolean combinational circuit is built from Boolean combinational elements that are interconnected by wires. So what are the elements? Well, there's three basic logic gates. So this is what a NOT gate looks like. Okay, so that, or it's sometimes called a logical inverter. So this just inverts the input. So if a true or 1 comes in, the output will be 0 or false. If false comes in, it produces output of true. Okay, so this is a truth table that would describe the input and output relationships. This is the visual of what an AND gate is represented by. Okay, the AND, for an AND gate, recall the logical AND, the only time the output will be true is if both of the inputs are true. Okay, so the only way to get an output of 1 is if both x and y, both inputs are 1. And then an OR is visualized in this manner. And recall a logical OR, the output is 1 if at least one of the inputs is 1, or if at least one of the inputs is true. Okay, so here, these are cases where I have one input being true, the output is 1, or both of the inputs could also be true to get an output of true. So those are the three basic gates, and that's how they work. So I can, string these together in any kind of combination to build a circuit or a Boolean combinational circuit. And the circuit satisfiability problem is if I have a Boolean circuit, like let's say visualized like this, that's got NOT gates, it's got AND gates, it's got OR gates in it, and is there a way for me to assign values to the inputs so that the output would be 0? That's what satisfiable means. Sorry, did I say 0? 1. So that the output is 1 or true. So is there a way for me to assign values to the inputs to make the output be 1? That's what satisfiable is. And here's an example of a circuit that is indeed satisfiable, because if we make the input x1 be 1, x2 is 1, x3 is 0, if you follow through, then the output of the circuit will be 1. So this is an example of a satisfiable circuit. Okay. So that is the problem that we want to show is NP complete. Okay, so recall, we have to show that it's two things. First of all, we need to show that it's in NP. And that is the purpose of Lemma 34.5, that the circuit satisfiability problem, which we'll call circuit sat, belongs to the class NP. So remember, something belongs to the class NP if we can verify a certificate or a solution for it in polynomial time. Okay, and so that's what we need to do. So our goal is to provide a 2-input polynomial time algorithm A that can verify circuit sat. Okay, if I were to draw a picture of this, okay, I have an instance of circuit sat. an instant of a circuit set has two things. It has a circuit, C, and then it has a certificate. I'll just call that Y. Okay, and what we want to do is verify that Y is actually a valid solution for C. Okay, so this is basically our input, and then we have this algorithm A. Okay, so we're trying to construct this polynomial algorithm. Okay, it gets a circuit C and whatever the certificate is, and then we need to, have an output of either yes or no. Yes, Y is a certificate for C, or no, it's not. Okay, and we need to do that all in polynomial time. Okay. All right, so what is this algorithm A, and how could we make that algorithm? Okay, so that algorithm would just go to each logic gate that's listed in the combinatorial circuit, okay, and then we would check that the values provided by the certificate on the output wire is correctly computed as a function of the input wires. Okay, so if I go, that circuit consists of some NOT gates and some AND gates and some OR gates, and then this certificate will tell me what the the values of the inputs and the outputs are. And so we would have to go to each gate and say, oh, according to the inputs that were assigned by Y, okay, does the output of that gate match the inputs? Okay, so that would be the first thing. We may have to make sure that Y is actually consistent with the circuit. Okay, and then after we see that it's consistent with the circuit, then we just have to check, okay, well, did it answer yes or no? So if it answered yes and it accepted it, okay, then we know that it's a valid solution. Or if it answered no, we know that Y is not a valid solution. So we can verify whether it is a correct solution by just checking that the inputs correspond to the outputs. Okay. Okay, so that's the way the algorithm works. Okay, but of course we still need to consider whether it runs in polynomial time. Well, the circuit has a certain number of gates, and for each gate it's going to just take us essentially, I can just go and check the inputs and the outputs essentially in constant time to see if they match up. Okay, so we can definitely do this in polynomial time. We just have to run through every gate and check that the inputs and outputs match according to what we get from Y. Okay. And there's no way for the algorithm to be fooled, okay, into believing that the circuit is satisfiable when it's not. We are just, when we check the inputs and the outputs based on whether the output is a 1, then the algorithm answers yes, it is satisfiable. If the output is 0, it's no. And there's no way for us to get an output of 1 if the circuit isn't satisfiable. Okay. Okay, so that verifies that indeed the circuit is verifiable in polynomial time. Okay, we just check all of the inputs, make sure they correspond to the outputs that are in the certificate. The next thing we need to do now is show that circuit satisfiability is NP-hard. So NP-hard, we have to show that any language in NP can be mapped to circuit satisfiability. So if I were to draw a picture of this one, okay, I have this could be any language, or problem L. Okay, and I have an instance, and I have a string X. Okay. And I'm going to take X and see if it's an L. And the X is going to be an L if and only if. So this is kind of the stuff that's going to go in. Okay. And then what's going to come out, if this is some kind of a mapping here, is an instance of circuit sat. So over here we've got circuit sat. Okay, so I have a language L, okay, and I take an instance of that, and I'm going to map it to an instance of circuit sat. And this instance is, okay, of the language, okay, I'll accept the input for this one if and only if this circuit is satisfiable. So this, again, there's just going to be this mapping. I'm going to take a language, and I'm going to describe how to map it into a circuit satisfiability problem, so that this a input to this language is accepted if and only if this circuit is satisfiable. So this is this mapping that I need to create. Okay, so we need to describe a polynomial time algorithm. We're going to call it F. So this mapping is going to be F. Okay. And it's going to compute this reduction. So this mapping is, that's what a reduction is, this mapping. So it'll map every binary string X, okay, so X into a circuit C. So this is a circuit C. Okay. So that this X is in this language if and only if this circuit is satisfiable. Okay. So how are we going to do that? Well, this mapping is going to actually use an algorithm that checks, that we talked about, this algorithm that we talked about on the last page. Okay, so we know that there's some kind of an algorithm that can take a circuit and a certificate for a circuit and then verify in polynomial time whether it's satisfiable or not. Okay, and so that algorithm A is going to be used in this mapping. Okay, and the idea here, so we have an algorithm F that we're going to construct. This F is this mapping, and it uses the algorithm A, okay, in part of its reduction and part of its mapping. So let T of n denote the worst case running time of algorithm A. Okay, so let me write, so algorithm A is going to be used in here. There's algorithm A in there. On a length n input strings. And then K is the degree of the polynomial. Okay. And we'll also say that the length of the certificate that algorithm A runs on is also upper bounded by n to the k as well. Okay, it has to be because the algorithm runs in polynomial time, so the certificate can't be larger than that. Okay, so we're going to represent the computation of this algorithm as a sequence of configurations as the program that implements this algorithm is running on a specific machine. So imagine we would have, if we were going to run this, we would have the algorithm, and we could represent that as some kind of binary input. And if it was running on the machine, we would need to keep track of some things. So we'd have to keep track of like the program counter, the state of the machine, that's the machine state, the input that's coming in that we're checking, that's X, the certificate, Y, that needs that, and then any kind of working with storage that's part of the machine. Okay, so this is like memory, this is storage. Sorry, it's hard to see that. Okay, so all of this, okay, we would need to know, and then there's some kind of circuitry for the specific machine that the algorithm would be running on, and we're going to call that M. So this M is some kind of implements the circuit of the machine that the program is running on. Okay, and so we're going to think about so we're going to take all of this stuff. Okay, so this is a circuit right here, because that's, you know, a computer is just logic circuits, right? It's just a bunch of ands and ors and NOT gates. Okay. And so we would feed all of these inputs into the circuit that represents the machine that our program is running on. And now normally we think of a machine, you know, there's things like like the memory kind of the program counter goes through something and feeds back and changes the program counter. The memory kind of feeds back and changes the memory, that kind of thing. But rather than having it feed back on itself and change the variables like program counters and memory, we're just going to have a separate state for each one. So whatever, the circuit produces some kind of output, and it's going to change the program counter. So I'll say like this is our initial state, and then I'm going to have this whole new state. So this is like the new program counter that maybe gets incremented to go to the next instruction, and so on and so forth. This is the memory. Okay, we're gonna save the algorithm, the program counter, its state, the input x and y, and the memory. Okay, and so that would be state 1, and then we'd feed that into the same circuits that represent the machine. And so we're gonna have a whole bunch of these that we're gonna string together. Okay, for one, so this is the state when we start, and after one step of the algorithm, this is the state, and after another step, and another step, and another step, and we're going to do that many, many times until the algorithm completes, and we'll have a final state at the very end. That will be considered like the last state will be, and we know that the running time is t of n, so that we're only going to have tn, or in a polynomial number of these states that we have to keep track of. Okay, so that's kind of how this mapping is going to work. So here's kind of a visualization of that. So we've got these different states that keeps track of, it has the program itself, the program counter, the machine state, the input string, the certificate, and then memory, the working storage, and then this M is the circuitry that implements the machine that it's running on. And we're just going to take like T of n copies of this machine and keep track of its state one step at a time. So then the output, okay, is going to be stored in the working storage, the memory someplace, and there's going to be a distinguished bit in there that's going to have the final output of the algorithm, like the yes, that y is a valid certificate, or no, y is not a valid certificate. So there's some bit in the working storage somewhere that holds the answer that A computed. Okay, and that's going to be either a 0 or 1, and that will be the one that we're particularly interested in, okay, because that bit tells us whether language L accepted input X or not. All right, so the reduction algorithm, F, what it's going to do is we're going to give it an input X, and it has to compute or produce a circuit that's satisfiable if and only if there exists a certificate Y, so that the algorithm would accept Y. Okay, so this circuit that it produces will be satisfiable if X is accepted by the language, if it has a certificate, okay, and it won't be able to be satisfied if there isn't any kind of a certificate that would produce a 1. Okay, so that's our goal. So how is this algorithm going to work? Okay, well, it's basically going to do this, what this picture that we just drew says. So for input X, it's going to compute the length of X. That's going to be called N. And then the way that we're going to construct a circuit, we'll call that C prime, that has T of N copies of the algorithm is running. And then the input will be the initial configuration corresponding to running the algorithm on that machine. And then the output is going to be the T of N configuration. Okay, with that, remember, the algorithm runs for T of N steps, and after the last step, it'll be whatever the current configuration is. Okay, and then we're going to go and we're going to wire the inputs to C prime corresponding to the program A. So we're going to hardwire the whatever the representation for A is, we're going to hardwire the initial program counter and input X in the initial memory state. And so the only thing that remains that's not hardwired is the certificate to Y. Okay, so we see, you know, we've got this right here. So this is going to be hardwired. You know, I'll give it whatever the algorithm is. You know, we can take any algorithm and represent it as a bunch of ones and zeros. Okay, so those are just going to get hardwired in there. The program counter probably starts at, you know, 0. We'll save that the memory location starts at 0. Okay, we hardwire that in there. We hardwire the initial state of the machine in there. We hardwire the particular instance of X in there. Okay, the working storage. The only thing that's not hardwired in there is Y. Okay, so Y is going to come in as a separate input. Okay, so C prime is all of this stuff that's hardwired except for Y, and all these copies. Okay, so this part right here is C prime. So the only remaining input that's not hardwired, like we said, is a certificate. And then to create the circuit C, we're going to ignore all of the output from C prime except for that last bit, and that will be the output of C. Okay, so if we think about, you know, this is C prime, and then C is this circuit right here where we take this one bit and we're going to call that the output of C. Okay, so this is the input to the circuit, Y, and then this is the output of the circuit. Okay, now definitely this is a circuit. Okay, see, we've got wires that connect this circuitry and this circuitry and this circuitry and this circuitry, right? This is just whatever implementation of the machine that it's running on. So this is definitely a Boolean circuit. Okay. So that's the way that we create that circuit, that reduction. All right, so we need to convince ourselves that f correctly computes a reduction function. So essentially we have to show that that circuit that we've created is satisfiable if and only if there exists a input or a certificate Y, so that the algorithm A would produce a 1 output. Okay, so you know, if Y is an invalid certificate, it will produce a 0. If it's a valid certificate, it would produce a 1. Okay, so suppose there is a certificate such that the output would be 1. Well, if we take and we apply that certificate as the input to our circuit here, so if we apply that certificate, well, algorithm A is, we know that it in polynomial time will, if this is actually a certificate for X, then it will output a 1. Okay, so if Y is a certificate and is satisfiable, it will output a 1. Okay, let's say there isn't any possible certificate that can be produced for X. Okay, so no matter what Y we put in there, there isn't a certificate X, so it'll always output a 0. So this circuit is satisfiable only when there is a certificate that is valid for X. So, okay. So that's what this is all saying. So the F does correctly compute a reduction function. The last thing we need to convince ourselves is that it does so in polynomial time. Well, the number of bits used to represent the configuration is a polynomial in n. The program has constant size. It doesn't matter how long the input is. The program just has constant size, so we don't have to worry about that. The length of the input is n, so the length of, and we know that the length of the certificate is n to the k. We also know that the algorithm runs for at most n to the k steps, because it was a polynomial algorithm. And so the amount of working storage required by the algorithm must be a polynomial in n as well. And the circuit implementing the computer hardware has a polynomial size and the length of the configuration. You sort of feel like it should be constant, except that it has to implement the logic for the memory. Okay, and that memory is based on what the input is, and so it will be polynomial in the size of the input. Okay, that's why it's not constant. There are certainly a constant number of and or gates just kind of for implementing the processor part of the machine, but the memory has to be based on the input size or the configuration. So that's where that's why it's polynomial in the length of the configuration. Okay, and we know that we have a polynomial number of copies of that machinery. Okay, and so we've got a polynomial times a polynomial, which is another polynomial. It will be polynomial in n as well. So we can indeed construct that circuit in polynomial time. Okay. All right, so now that means that circuit satisfiability, okay, every possible NP language can be reduced to circuit satisfiability, and therefore, and we already showed that it was NP in NP, so this is our very first NP complete problem. And so in the future videos I will do some reductions using like circuit satisfiability and other ones. We'll just have to do a mapping between one language or problem and another one. We won't have to do it for every language like we did for circuit satisfiability.